Hi, folks. This is Larry Mussolino. I wanted to record another video for Module 8 in STAT412. This is part 2 on a few other hypothesis testing type problems in Module 8. So we've already talked about hypothesis tests for two means. And if you remember, if you're given summary data, that means you're given like the sample mean and sample standard deviation. This is a worksheet you can use here in Excel. If you're given raw data and you want to compare two means, there's built-in Excel functions under data, then data analysis. And that was part 1 of this video. So for examples of those, please go back and look at the Module 8 video part 1. There's another type of test that was called a contingency test. And you remember, this is testing if there's independence between two qualitative variables. Here was an example. We wanted to know, is there any dependence between stretching or not stretching and minimizing injuries? Another way we could say this is, do injuries depend on stretching or not stretching? So this was called a hypothesis test for independence. It was set up using a table like this that's called a contingency table. And again, I did some of these examples in the part 1 of the video. I'll do another one of these in a little bit. But what I wanted to go to next was this example that we're looking at right now. This is question 17 on the homework. And this has to do with something called a goodness of fit test. So let's read this over and see what they're asking us. It says, for a recent year, the followings are the number of homicides that occurred each month in a city. Use 0.05 significance, remember that means alpha equals 0.05, to test the claim that homicides in the city are uniformly distributed. Now, what uniformly distributed means is about the same number of homicides occur every month. So I want to compare this actual data. So think of this as the actual data and the expected data is going to be about the same number of homicides each month. That's what they mean when they say uniformly distributed. All right, well, there's a setup for this test. And first, of course, we're going to start out with the known alternative. Now, in this Excel workbook, a copy of this workbook is posted in course announcements. There's a tab down here called Goodness of Fit. So I'm going to click on this Goodness of Fit test. All right, so I'll show you how to set this up in a second. Now, it turns out that the setup of the null and alternative here is always the same for this kind of a test. The null hypothesis says that the frequency distribution fits what you expected to see. The alternative hypothesis says that the frequency distribution does not fit. I think I have a typo here. Let me fix this. This should say does not fit the expected distribution. Okay, well, for our example, the way we're going to say it is the null hypothesis is that the distribution of the number of homicides is uniform. And then the alternative would be the distribution of homicides is not uniform. So again, the null hypothesis is always assuming that the frequency distribution fits what's expected. The alternative is always stating that the frequency distribution does not match what is expected. All right, well, the way to set this up is to create two columns. So I'm going to copy this data into Excel. So let me come here to my lab here. I'm going to copy to the clipboard. I'm going to take this data and copy it. And I'm going to come here and copy this into Excel. Okay, so I just copied these numbers into Excel. Whoops, I think I copied it incorrectly. Let me go back and redo that. Let me copy it here, I think is what I wanted to do. All right, there we go. So we copied the data in Excel. Now, what I need to know is what is the expected? By the way, reminder, in these Excel workbooks, you enter data in the yellow boxes and the green boxes are going to get automatically populated for you. All right, well, the first thing I did is I just added up this column. This is the number of homicides, and it looks like there were 517 homicides over the entire year. Well, I wanted to figure out what's expected. Well, remember, expected is that it's uniform, meaning the same number of homicides every month. So if I click my mouse here, if you notice the formula is just taking cell B15 divided by 12. Well, that's the yearly sum divided by 12. So that's just a way to easily calculate that I'm expecting the 517 homicides to be evenly distributed, same number per month. All right, well, then what we're going to do is calculate the test statistic. And here is the test statistic right here. Works out to be 10.466. And if you notice, the test statistic is really summing up. Here it is. It says sum E3 to E14. So the test statistic is summing up this column. So it's just the sum is 10.466. So we call that the test statistic. And this Greek symbol is called chi. So we call this the chi-squared test statistic. How are these chi-squared numbers being calculated? Well, the formula for each row is you take the actual, let me click on a cell here so you can see it. I'm going to click on this first green cell right here. So if you notice, what this is doing is it's taking the actual number minus the expected number, squaring that quantity and dividing by the expected. Let me do it for the first row, just so we can see what the calculation looks like. For the first row, I'm going to take the actual. Well, that was 37 homicides. I'm looking at January now, right? So this is January. The actual number of homicides is 37. Subtract what I expected. That's 43.083. Square that quantity divided by the expected. So I'm going to divide by 43.083. If you work this out on your calculator, you get 0.858962. So that's where this number is coming from. Well, I do that same calculation row by row. Add up these numbers. That's how we're getting this test statistic. The last thing I need to do is calculate the p-value. Well, there's a nice built-in command in Excel to do this. It's called chi-squared test. And the way it works is for the p-value, you work out chi-squared.test. And then I've got to tell Excel where is the expected numbers and where are the actual numbers. So for us, in this example, the expected are the yellow numbers. So that's going to be what? B3, cells B3 to B14. The actual numbers are in column E, so it's going to be E3 to E14. And Excel calculates the p-value. Okay, well, in this example, actually, let me show you the, this cell. I'm going to click right here. And you can see it says chi-squared.test up here. B3 to B14, that's the expected range, comma C3. I'm sorry, I made a mistake here. I should have said in my, this should be C3. Sorry, the actual is in C3 to C14. Yeah. And by just executing this command in Excel, it gives me the p-value. All right, so we have the p-value now. We're ready to go and do the final step here. Do we reject or fail to reject? Well, let's do a comparison. Our p-value here is 0.489. Alpha was given in this problem as 0.05. Well, our p-value is way bigger than alpha, right? 0.489 is a much bigger number than 0.05. Well, here's my decision. If the p-value is greater than alpha, our decision is fail to reject null. Okay. And when you fail to reject the null, you really don't have enough evidence. So I'm going to come here and say, fail to reject the null. There is insufficient evidence, right? There's not enough evidence. So that's going to be my decision. Okay, so this goodness of fit test calculator here will help you set up the two columns you need. You need the actual, the expected, and then you do this calculation here in column E. That calculates the contribution to the chi-square test statistic. The test statistic is adding up this column, and then the p-value you can calculate using that chi-square.test command in Excel. Okay. Again, this Excel spreadsheet is available to you, so please feel free to use this for any of the homework or quiz questions. All right, maybe we should do another one of these while we have this calculator available. Let's do this one. This one's going to be similar. All right, so this one says randomly selected birth records were obtained. Test the claim that births occur with equal frequency on different days of the week. So this is, testing out that there's about the same number of births on Monday versus Tuesday versus Wednesday, so on. All right, well, I'm going to use the same Excel calculator here. I'm going to have to modify things a little bit because, this is not going to be 12 months. It's only going to be 7 days of the week, but I can do that. So I'm going to come here first, and I'm going to copy this data to the clipboard. And I could see it's just going to be 7 rows. So I'm going to copy it here, and I'm going to copy it right here. All right. Well, of course, my data only goes from Sunday to Saturday here. These other rows are not needed, so I'm going to delete these rows. So let me get rid of these rows. All right, so I got rid of those rows. All right, well, the sum of the births here is 370. So I've got to take that 370 and evenly distribute it across the 7 days of the week. So I'm going to come here and take that sum and divide it by 7. And I'm going to copy that cell down here. So now I have the expected births for each day of the week. All right, here's the contribution to the chi-square in these green boxes here. Here's the test statistic, 5.503. Right, remember the test statistic is just summing up these numbers. So we know the test statistic is 5.503. The p-value is this chi-square test command. Let me show that to you one more time. I'm going to click here, and it's chi-square.test, B3 to B9. If you see up here, B3 to B9, that's the actual data. C3 to C9 is expected. So when I work that out, the p-value is 0.481. All right, so let's come to a final decision. Our p-value here is 0.481. Our alpha value, and this one they told us to use alpha equal 0.01 for significance. So alpha here is 0.01. Well, 0.48 is much bigger than 0.01. When the p-value is greater than alpha, our decision here is fail to reject the null. When you fail to reject the null, there's not enough evidence. So fail to reject the null, there's insufficient evidence to reject the claim that births occur with the same frequencies. All right. Yeah, there's one other question here. Why would you maybe expect to see lower births on Saturdays and Sundays? Well, there is this aspect of induced births. Sometimes they can actually schedule the birth, and of course they would, a doctor or hospital would probably not schedule on the weekend if possible. So that would explain a dip in Saturday and Sunday births. All right, so that's that one. Let's see here. Let's do this one. This one is a little different because in this one, they're giving us the proportions. So let's read this one over. It says the table below lists the number of games played in a baseball championship, along with the expected proportion for number of games. So it looks like what they're giving us here is that the actual games played is 4, 5, 6, and 7. There was actually 20 of those kinds of games. But what's the expected number? That's what we need. Well, we don't know that, but we can calculate it ourselves. So I'm going to make up a little table down here to help organize our data. So let me do this. Let me come down here to Excel. All right, and let me just type in here games played. Actually, let me copy the data. I think I could do that. Yeah, that's easier. So let me just copy the data down here. All right, so we have this data. And what I'm going to do is I'm going to copy this data up to our Excel table up here. So I'm going to copy that data there. Okay. I'm going to get rid of Thursday, Friday, and Saturday now because those rows don't make any sense for us. Okay, delete those rows. All right, so here is the actual data that we collected. I'm going to highlight that in yellow so we know it. Now, here's the complicated part. What am I going to do for these expected numbers? I got to figure that out. First, let me sum up the number of contests. It looks like there's 98 altogether. All right, well, what I have to do now is take into account what I expect for each row. And I'm going to copy these expected proportions up here so we have them there. So let me come to this first green cell here. What am I expecting for this row? Well, there were 98 contests altogether. So I'm going to reference that as B7. So I'm going to do $B, $7. By the way, the dollar signs make it an absolute reference. So when I copy it, it's going to stay as cell B7. And I'm going to multiply that by the proportion that I'm expecting. That's this 0.125. And I'm going to copy that formula down. So what it's telling me is for 4 games played, there were actually 20 of them. I was expecting 12.25 of them. For playing 5 games, there was actually 19 of those kinds of contests. I was expecting there to be 24.5. So what I did here is I took the total 98 and multiplied it by this expected proportion value to come up with the actual expected number of contests. All right, well, I think I have what I need then. Here's the test statistic, 12.114. Here it is. And here's the p-value, 0.007. All right, let's come to a final decision now. In this case, the p-value is 0.007. They told us to use an alpha of 0.05. Well, this p-value is less than alpha, right? 0.007 is a number less than 0.05. Well, if the p-value is less than alpha, your decision is reject the null. So we're rejecting the null hypothesis. And when you reject the null, there's enough evidence. There's sufficient evidence. So here it is, reject the null. There's sufficient evidence. All right, so we used this goodness of fit testing calculator here. It helped us out. I think we just did number 17, number 18, and I think we did, what other, did we do number 19 yet? Yeah, and we did number 19. All right, let's see what else. Did we do number 20? I don't think so. Let's look at number 20. All right, let's look at this one. It says, in a study of high school students, researcher obtained survey results from this table. Use a 0.05 significance level, that's alpha, to test the claim of independence between texting while driving. And so I'm noticing this is a test of independence. So I'm going to come here to contingency table analysis. Remember, this was how you conduct a test for independence. And let me open up this data set here. So I'm going to click right here. And I'm going to just copy these numbers here. So this is, I'm just going to type this in, yes, no, for driving with alcohol. And this is texting and no texting. And here are the numbers, 730, 3021, 155, and 4544. Okay, so I got that data copied in. And again, what we're trying to do is ask ourselves, is there a relationship between these two variables, texting and driving under the influence of alcohol? All right, well, this Excel calculator worked out the test statistic for us. Here it is, a very large number, 581. What that tells me is when the test statistic is very, very large like this, it tells me there's a large difference between what I observed and what I expected. Well, here's the p-value, 0. Remember, when you set up the null and alternative, the null is always that the two variables are independent. So that's why we selected this one. Texting is independent of driving with alcohol. The alternative is the variables are dependent. So we're saying here texting and drinking alcohol are dependent. All right, so we're ready to come to a decision. In our case, the p-value is 0. Alpha was given to us in the problem as 0.05. Well, of course, 0 is less than 0.05. When the p-value is less than alpha, our decision is reject the null hypothesis. When you reject the null hypothesis, there's enough evidence. So I'm going to come down here to the answer choices, and we're going to reject the null. There is enough evidence. There is sufficient evidence. Okay. Folks, hope this is helpful. Again, this Excel spreadsheet is posted in course announcements. There's also video number 1 posted in course announcements as well. This is video number 2. All right, folks, let me know if there's any questions.